Hey, what's up everybody? In this video, I'm going to take a few moments to discuss electrophilic aromatic substitutions. Specifically, I'm going to be talking about the Friedel-Crafts alkylation. Now, the Friedel-Crafts alkylation is basically a type of reaction that allows you to put alkyl groups onto aromatic ring systems. So, let's say we had benzene. Now, if we took this benzene and we reacted it with an alkyl chloride, and we did this reaction in the presence of an aluminum 3 chloride catalyst, what we would end up with is something that looks like this. So here's our aromatic ring, it's our benzene ring. Now look at this group here, look at this alkyl group here. Notice that this alkyl group that's attached to the benzene ring is the same alkyl group that was present in our alkyl chloride. So we're pretty much going to take this alkyl group and we're going to swap it out with a hydrogen. So now, instead of having a hydrogen on benzene, we're going to have this alkyl group attached to our benzene ring. All right? Now, as a result of this reaction, we're also going to generate some HCl. And because aluminum 3 chloride is a catalyst, by the time this is all said and done, we should regenerate that aluminum 3 chloride. All right, so this is the reaction we're going to be talking about today, the Friedel-Crafts alkylation, just another type of electrophilic aromatic substitution reaction. With all of that in mind, why don't we go ahead and discuss the mechanism. Now, like many of the other electrophilic aromatic substitution type reactions, very first thing we need to do is we need to generate an electrophile that is sufficient for EAS. We need to generate an electrophile that is sufficient for electrophilic aromatic substitution. And here's how we're going to do it. We are going to take our alkyl chloride and we're going to react it with our aluminum 3 chloride catalyst. Now, our alkyl chloride is actually going to act as a Lewis base, an electron pair donor. So this alkyl chloride is going to act as a electron pair donor, a Lewis base, and it's going to donate electrons into this Lewis acid here, right? This aluminum 3 chloride is going to act as a Lewis acid, an electron pair acceptor. So, lone pair on this chlorine atom here, the chlorine in our alkyl chloride, this lone pair is going to form a coordinate covalent bond with this aluminum. And as a result of that coordinate covalent bond forming, we're going to get a Lewis adduct, a Lewis acid base complex. So right here, that's our coordinate covalent bond. Just to remind everybody what a coordinate covalent bond is, the type of covalent bond, it's a special type of covalent bond in which both electrons in the bond originated from the same atom, all right? So we have this coordinate covalent bond form. We have this Lewis acid base complex. Notice that this central aluminum atom now has a formal negative charge associated with it. Similarly, the chlorine atom with the alkyl group attached, yeah, this chlorine atom now has a positive charge associated with it. All right, so in the first step, Lewis base reacts with Lewis acid to give us a Lewis acid base complex. Now, in this next step, this is actually how we're going to generate our electrophile. Take a look at this bond right here. So we have a carbon-chlorine bond. Now, the electrons within this bond, they're going to fold back on the chlorine atom, and that's going to give us two different chemical species. Number one, it's going to give us this AlCl4 minus. This is sort of the remnants of our Lewis adduct, right? And it's also going to give us a tertiary carbocation. If you think back to carbocation stability, tertiary carbocations are actually pretty stable, right? So this tertiary carbocation is actually going to serve as our electrophile. So now that we have this electrophile, this tertiary carbocation, we are now ready to begin electrophilic aromatic substitution. So benzene is going to come by. And as usual, I drew in a hydrogen on this benzene. Now, these pi electrons here within the aromatic ring system, these pi electrons are going to reach out and grab this carbon. So now we're going to get a bond between this carbon in our ring and this carbon in our electrophile. Right? So we formed a bond between the carbon in the ring and the carbon, the central carbon, in our electrophile. And in the process of doing this, again, I just want to remind you all, we had something that was aromatic, but we're going to break aromaticity when we form this bond. So now we have something that's not aromatic. We have our uranium ion. Remember, the uranium ion is a reaction intermediate that's characteristic of virtually all electrophilic aromatic substitutions. Now, because we broke aromaticity in this step, in order to finish things off, we have to restore aromaticity. And here's how we're going to do it. Remember, the hydrogen connected to the carbon, connected to our electrophile. It's that hydrogen that's going to become deprotonated. So do you remember this AlCl4 minus that we made earlier, this sort of the remnants of our Lewis acid-base complex? So it's going to come by and it's actually going to help us with this deprotonation step. So pick any aluminum chloride bond, doesn't really matter. I picked this bond here. The electrons in this bond are going to reach over and grab this hydrogen. All right, so we're going to form a bond between a chlorine atom and a hydrogen. All right. Now, when this happens, the electrons in this bond here, this hydrogen-carbon bond, those electrons are going to fold back into the ring system. Now, as a consequence of this step here, we're going to generate a few things. Number one, if a bond forms between Cl and H, that's HCl, right? So we're going to get some HCl here, some hydrochloric acid. So here also we have AlCl4 minus. Now, if we break this bond, we have AlCl3, right? So we regenerated our aluminum 3 chloride catalyst. And because we have this deprotonation step here, we're going to restore aromaticity. That's going to give us this chemical species here. All right? So again, let's just quickly recap everything we learned today with regards to the Friedel-Crafts alkylation. First thing, we need to generate an electrophile that is sufficient for electrophilic aromatic substitution. So to do that, we're going to take our alkyl chloride, and that's going to act as a Lewis base, an electron pair donor. And we're going to react that with a Lewis acid, our aluminum 3 chloride catalyst. That's going to give us a Lewis adduct, a Lewis acid-base complex here. Now, this Lewis acid-base complex is actually going to break apart into two different chemical species, one of them being our electrophile. So then once we've generated our electrophile, our aromatic ring system is going to come by, form a bond with this electrophile. In the process of forming that bond, we're going to break aromaticity. But through a deprotonation step here, we're going to restore aromaticity, all right? Just to summarize a few things, just to bring up a few other really important points. Notice that this alkyl chloride here is a tertiary alkyl chloride. Now, if it was a secondary alkyl chloride, the mechanism would probably be pretty much the same. However, if this was like a primary alkyl chloride, the reaction mechanism would be slightly different. So I'm probably going to post a separate video on the Friedel-Crafts alkylation involving primary alkyl chlorides. But anyway, there you have it, the Friedel-Crafts alkylation involving a tertiary alkyl chloride. Let me know if you have any questions. Just leave them in the comment section below. And stay tuned because there's still a lot more to talk about with regards to electrophilic aromatic substitution. So with that being said, Thanks for watching and have a great day, everybody.